6. The matrix bridge. In the previous scene, we discovered that the Hurwitz lattice can be organized into 4 cosets of D4, 4 families, 1 underlying structure. But we were left with a question. Can one transformation take the entire Hurwitz lattice into the D4 lattice? The answer is yes, and the transformation is remarkably simple. It is a matrix. Let us call it M, applied to a Hurwitz vector, x. Y is equal with M multiplied by x. The first thing we might expect is an ordinary rotation. But there is an immediate problem. The shortest non-zero Hurwitz vectors have squared norm 1. The shortest D4 vectors have squared norm 2. A genuine orthogonal transformation cannot change a vector's norm, so a rotation alone cannot do the job. Something else is happening. The matrix is orthogonal, but with a scale factor. In other words, M transposed M is equal with 2i. Therefore, M multiplied by x, all squared, is equal with 2x squared. The transformation preserves angles and the overall geometry, but doubles every squared norm. This is a similarity transformation. And now the difference between the 2 lattices suddenly makes sense. A Hurwitz unit has squared norm 1. After applying M, its image has squared norm 2. Exactly the norm of a D4 root. The apparent mismatch was not a problem. It was the clue. Now let us see what the matrix actually does to the lattice. Take an integer Hurwitz vector. The coordinates of its image are integers. More importantly, their sum is even. Therefore, the image belongs to D4. Now take a half-integer Hurwitz vector, apply the same matrix. Again, the resulting coordinates are integers. And their coordinate sum is even. So the half-integer part of the Hurwitz lattice is sent into D4 as well. Every Hurwitz integer maps into D4. But that only proves containment. We still need the reverse direction. Suppose we start with an arbitrary point of D4. Apply the inverse transformation, M inverse. The resulting coordinates come in matching parity pairs. If the relevant coordinates have the same parity, the resulting entries are integers. If they have opposite parity, they are half-integers. And the parity condition on the D4 point guarantees that the 4 coordinates are either all integers or all half-integers. In other words, M inverse applied to D4 is included or equal with H. So, we have both directions. M applied to H is equal with D4. The correspondence is therefore a bijection. Every Hurwitz integer has exactly 1 image in D4, and every D4 point has exactly 1 Hurwitz preimage. The 4-coset structure has been compressed into a single linear transformation. Now let us test the most important shell. The Hurwitz shell of squared norm 1 contains exactly 24 points. These are the 24 Hurwitz units. Apply M. Every one of those 24 points moves to a vector of squared norm 2. And those images are precisely the 24 roots of D4. The regular 24 cell has appeared on the other side of the transformation. The 24 Hurwitz units and the 24 roots of D4 are the same 24 cell viewed through 2 different coordinate systems and 2 different scales. 8 of the Hurwitz units have integer coordinates. They correspond to 8 D4 roots. The remaining 16 Hurwitz units have half-integer coordinates. They correspond to the other 16 roots. So the matrix does something remarkable. It does not merely map one collection of points to another. It converts the integer or half-integer description of the Hurwitz lattice into the parity-based description of D4. And it does so for the entire lattice, not just the 24 cell, not just the shortest vectors, every Hurwitz integer, every D4 point. There is one more way to understand this transformation. The same bridge can be expressed intrinsically using quaternion multiplication. The matrix description and the quaternion description are two realizations of the same map. So now three perspectives come together: arithmetic, geometry, and quaternion algebra. The four square representations generate the shells. The Hurwitz integers provide the quaternionic structure, and the matrix M provides the bridge to the D4 lattice. The correspondence we were looking for is no longer a conjecture. It is a bijection. It is a similarity, and it doubles the squared norm. But there is an important warning. A lattice correspondence is not automatically a multiplication correspondence. The fact that M maps H onto D4 does not mean that ordinary quaternion multiplication can simply be performed on D4 coordinates. The coordinates have been transformed. The geometry has been preserved up to scale, but the algebraic multiplication law has not automatically come along with them. And this distinction will become crucial, because our next question is no longer, how do we map the lattices? We already know the answer. The next question is, what happens to multiplication under this map? That is where the story becomes much more interesting. Seven. Why coordinates aren't enough for multiplication. In the previous scene, we established a remarkable correspondence. The Hurwitz lattice maps bijectively onto the D4 lattice. The 24 Hurwitz units map to the 24 roots of D4. Geometrically, the two descriptions give us the same 24 cell. But now we have to ask a different question. What happens to multiplication? This is where the distinction between geometry and algebra becomes essential. Start with the 24 Hurwitz units. They are the elements of the Hurwitz lattice with norm 1. There are exactly 24 of them. 8 have integer coordinates. 16 have half-integer coordinates. Together, they form the vertices of the regular 24 cell. But they have another property. They are closed under quaternion multiplication. Multiply any two Hurwitz units, and the result is another Hurwitz unit. The 24 elements form a finite multiplicative group. This group is the binary tetrahedral group, usually denoted 2t. So in the Hurwitz coordinates, closure is exact. Now let us apply our matrix correspondence. The 24 Hurwitz units become the 24 roots of D4. Geometrically, nothing has gone wrong. We still have the same 24 cell. But now suppose we forget where these points came from. Suppose we simply look at their D4 coordinates and interpret those four coordinates directly as quaternion coefficients. Then we try ordinary quaternion multiplication. This is where something surprising happens. Take two roots, multiply them as ordinary quaternions. The result does not necessarily belong to the set of 24 roots. The product can leave the root set. So we have apparently lost closure. But did the group disappear? No. The group was never a property of the coordinates alone. The problem is the multiplication law. Our map M is a linear similarity between lattices. It is not a quaternion algebra homomorphism. In general, M Q1 multiply with Q2 is not equal with M Q1 multiply with M Q2. That single distinction explains everything. The matrix changes the coordinates. It preserves the geometric structure up to scale, but it does not preserve the original quaternion multiplication law when the transformed coordinates are interpreted naively as quaternion coefficients. So the correct question is not, are the D4 roots closed under ordinary quaternion multiplication? The answer is no. The correct question is, can we transport the Hurwitz multiplication onto D4? And the answer is yes. The construction is simple. Take 2 points in D4. Call them X and Y. First map them back to Hurwitz coordinates, M inverse X and M inverse Y. Now multiply those two Hurwitz quaternions. Apply M to the product of M inverse X and M inverse Y. Finally, map the result back into D4. take the inverse of m applied to x, take the inverse of m applied to y, multiply those two results together, apply m to that product. This defines a new multiplication on D4. Apply the inverse of m to x and to y, multiply those two results together using quaternion multiplication, and then apply the map m to the product. Notice what we have done. We have not changed the underlying group. We have changed the way multiplication is expressed in the new coordinates. The procedure is, apply the inverse m to the lattice D4, which lands inside the larger set H, take two elements from H, and multiply using quaternion multiplication, and the result stays inside H. Apply the map m to an element of H, which sends it back into the lattice D4. So the multiplication in D4 is not the ordinary quaternion product of its coordinate vectors. It is the product transported through the bijection. And because the Hurwitz units form a group, the transported operation is automatically closed. The 24 roots therefore support two different structures. As points in four-dimensional space, they form the vertices of the regular 24 cell. As elements equipped with the transported multiplication, they form a group isomorphic to the binary tetrahedral group. The geometry is unchanged. The coordinates have changed, and the multiplication law has changed with them. This distinction is fundamental. A coordinate transformation can preserve lengths, angles, adjacency, and the entire combinatorial structure of a geometric object, without preserving the algebraic operation originally attached to its coordinates. So when we say that the D4 roots correspond to the Hurwitz units, we must be precise. They correspond as points. They correspond as lattice elements. And they correspond as group elements, only after the multiplication has been transported through the bijection. This gives us three layers of structure: geometry, the 24 cell, coordinates, the H or D4 representation, and algebra, the quaternion multiplication. These three layers are related, but they are not interchangeable. And that is perhaps the most important lesson of this chapter. The matrix bridge gives us the lattice correspondence. The quaternion structure gives us multiplication. And the transported product tells us how that multiplication appears after changing coordinates. So we have finally answered the question that remained at the end of scene 6. The 24 Hurwitz units are closed under quaternion multiplication. The corresponding D4 roots are not closed under naive quaternion multiplication, but they are closed under the multiplication transported through the matrix bijection. The geometry survives the coordinate change. The algebra must be transported with it. And this distinction will become the foundation for everything that follows. (8) The complete picture. We have now reached the end of the bridge. At the beginning of this chapter, the Hurwitz lattice and the D4 lattice appeared to be very different objects. One contains integers and half-integers. The other contains only integers. One has shortest squared norm 1. The other has shortest squared norm 2. And yet, beneath these differences, we discovered a precise correspondence. The key is the matrix M. It maps every Hurwitz integer to a point of D4, and it does so bijectively. M applied to H is equal to D4, but this is not an ordinary rotation. The matrix satisfies M transposed, M equals 2. Therefore, every squared norm is multiplied by exactly 2. mx squared is equal with 2 multiplied by x squared. This explains the difference between the two lattices. A Hurwitz vector of squared norm becomes a D4 vector of squared norm 2n. The scale difference is not an accident. It is built into the transformation itself. Now recall the 4 coset structure. The Hurwitz lattice is organized into 4 cosets of D4. 2 are integer cosets. 2 are half-integer cosets. Together, they make the complete Hurwitz lattice. So the apparently complicated mixture of integer and half-integer coordinates has a very orderly structure. 4 families, 1 lattice, and the matrix, M, brings all 4 families into the single parity-defined structure of D4. Now look at the smallest shell. The Hurwitz lattice has exactly 24 vectors of squared norm 1. These are the 24 Hurwitz units. Under M, they become vectors of squared norm 2, and these are precisely the 24 roots of D4. So the two descriptions give us the same regular 24 cell. On one side, 24 Hurwitz unit with norm 1 on the other. 24. D4 roots with norm 2. The matrix provides the one-to-one correspondence between them. The correspondence also explains the familiar division of the 24 Hurwitz units. 8 are the integer, or Lipschitz, units. 16 are the genuine half-integer Hurwitz units. Under the matrix correspondence, these become the corresponding 2 families among the 24 D4 roots. The geometry is the same. The coordinates are different. The scale is different. But the combinatorial structure is preserved. And now we can see the deeper picture. There are really 3 descriptions of the same mathematical structure. First, arithmetic, numbers represented as sums of 4 squares. Second, geometry, lattices, shells, parity, and the 24 cell. And third, algebra, Hurwitz quaternions and their multiplication. These are not 3 unrelated subjects. They are 3 views of the same underlying structure. The arithmetic tells us which points exist. The lattice tells us how those points are organized geometrically. And the quaternion algebra tells us how certain of those points multiply. But there is an important distinction. The matrix correspondence preserves the geometry, but it doesn't automatically preserve the quaternion multiplication. The 24 Hurwitz units are closed under ordinary quaternion multiplication. They form the binary tetrahedral group. But if we simply take the corresponding D4 coordinates and interpret them as quaternion coefficients, ordinary quaternion multiplication does not remain inside the 24 roots. So coordinates alone are not enough. The multiplication must be transported through the bijection. For x, y, belonging to D4, the appropriate product is obtained by going back to the Hurwitz lattice, multiplying there, and returning to D4. The geometry remains the 24 cell. The coordinates are D4 coordinates, and the multiplication is the Hurwitz multiplication expressed in those new coordinates. This gives us a complete conceptual picture. Arithmetic, geometric, quaternion algebra. The sums of 4 squares generate the shells. The Hurwitz integers organize those shells. The 4 cosets explain their parity structure. The matrix, M, provides the bridge to D4. The norm doubling property explains the different scales, and the transported multiplication explains how the quaternionic algebra survives the change of coordinates. What initially looked like 2 unrelated lattices is actually one structure seen from 2 complementary coordinate systems. The 24 cell is the geometric meeting point. The Hurwitz units provide its quaternionic interpretation, and the D4 roots provide its root lattice interpretation. We have therefore completed the bridge. But this is not the end of the story. It is the point where the story becomes more interesting. We now know how the 2 lattices correspond. We know how their shells correspond. We know how their 24 cells correspond. And we know that multiplication must be transported rather than naively reused. The next question is therefore no longer about finding the correspondence. We have found it. The next question is, what new mathematics becomes visible once we use this correspondence? That is where we go next. Nine. From arithmetic to geometry. We began with numbers. Numbers written as sums of 4 squares. At first, they seemed purely arithmetic. For each value of n, we searched for integer solutions of w squared plus x squared plus y squared plus z squared equals n. And when n was odd, another family appeared, the half-integer points. Together, these points formed the shells of the Hurwitz lattice. Then we discovered something unexpected. These shells were not random collections of points. They possessed a precise parity structure. The integer points separated according to the parity of their coordinate sum. The half-integer points formed two corresponding translated families, 4 cosets, 1 lattice, and underneath this structure was the D4 root lattice. At first, the two lattices looked different. The Hurwitz lattice allowed both integers and half-integers. The D4 lattice contained only integers with even coordinate sum. Their shortest vectors even had different lengths. But then the bridge appeared, a matrix, M, a single linear transformation that sends the entire Hurwitz lattice bijectively onto D4. MH equals D4, and it does something very specific to the norm. The norm of mx squared is equal with twice the norm of x squared. So, a Hurwitz shell of norm, n, becomes a D4 shell of norm, 2n. The apparent difference in scale was not an obstacle, it was part of the correspondence. Then came the most beautiful example. The 24 Hurwitz units, 24 points of norm 1, 8 with integer coordinates, 16 with half-integer coordinates. Together, they form the vertices of the regular 24 cell. Apply the matrix, and the same 24 points become the 24 roots of D4. A 24 cell of norm 2. The geometry has survived, only the coordinates have changed, and now the arithmetic, geometry, and algebra can be seen together. The arithmetic of sums of 4 squares tells us which points occur. The geometry of the lattices tells us how those points are arranged, and the Hurwitz quaternions tell us how the special norm 1 points multiply. These are not 3 separate stories. They are 3 descriptions of the same underlying structure. But there was one final subtlety. Coordinates are not multiplication. The Hurwitz units are closed under quaternion multiplication. The corresponding D4 coordinates are not closed if we simply reinterpret those coordinates as quaternion coefficients and multiply them directly. The multiplication must be transported through the correspondence. Map back. Multiply. Map forward. The geometry remains the same. The algebra is expressed differently, and that distinction is essential. So the bridge we have built is more than a change of coordinates. It connects 3 worlds: arithmetic, geometry, and algebra sums of 4 squares. The Hurwitz lattice, the D4 root lattice, the 24 cell, and the binary tetrahedral group, all connected by the same underlying structure. What began as a search through integer solutions has led us into 4-dimensional geometry and quaternion algebra. The numbers were never just numbers. The geometry was hidden inside them, and the algebra was waiting to be recognized. This is the bridge, and now that we have crossed it, we can begin to explore what lies on the other side. A framework. Emerging from the examples. We have now seen the same pattern appear again and again. Different values of n, different 4-square representations, different shells, and yet, beneath the details, the same structure keeps returning. The examples suggest that we can turn these observations into a general procedure, not yet a theorem, not yet a final answer, but a framework, a way of looking at every shell through the same mathematical lens. So let us begin with an arbitrary natural number. Our first step is purely arithmetic. Enumerate all representations of n as a sum of 4 squares, w squared plus x squared plus y squared plus z squared equals en. Every solution gives us an integer point in four-dimensional space, but we do not want to treat these points as an unorganized list. The second step is to group them by coordinate pattern. For example, patterns such as AAB0, 0 or AABC, 0 can generate entire families of points through permutations and sign changes. These families are the symmetry orbits of the shell. So instead of thinking of a shell as hundreds of individual points, we begin to see it as a collection of a much smaller number of geometric patterns. The arithmetic decomposition becomes a geometric decomposition. Now comes the second part. For odd values of n, there may also be a half-integer shell. To find it, we do not simply search for more ordinary integer solutions. Instead, we solve u squared plus v squared plus s squared plus t squared equals 4n with all four coordinates odd. Then we divide the resulting coordinates by 2. The result is a collection of half-integer Hurwitz vectors. So, the shell is enriched. The integer representations give us one part. The odd representations of 4n give us another. Together, they form the complete Hurwitz shell. The third step is to classify every point according to its coset. For an integer vector, we examine the parity of the coordinate sum. If the sum is even, the vector belongs to D4. If the sum is odd, it belongs to the complementary integer coset. The half-integer vectors occupy the corresponding translated half-integer cosets. So the entire Hurwitz lattice is organized into 4 cosets. The arithmetic points have now acquired a geometric address. And this gives us the fourth step. For every point in the shell, determine which coset it belongs to. We can now view the same shell simultaneously from several perspectives. As an arithmetic object, it is a collection of representations of n as a sum of 4 squares. As a quaternionic object, it is a shell in the Hurwitz integers. And as a geometric object, it is organized into symmetry orbits and lattice cosets. 3 descriptions. 1 shell. 1 underlying structure. This is the central idea emerging from our examples. Lagrange's four-square theorem tells us that every natural number has representations as a sum of 4 squares. Hurwitz arithmetic tells us how those representations sit inside the quaternionic lattice, and the geometry of D4 tells us how the points are organized by parity, symmetry, and coset. The shell becomes the meeting point of all 3. For a given, n, we can therefore imagine the following pipeline. N first becomes 4 square representations, then symmetry orbits, together with, when appropriate, half-integer representations, and finally, coset classification. The result is not merely a list of solutions. It is a structured geometric object, a shell whose arithmetic, quaternionic, and geometric descriptions reinforce one another. And this perspective changes the question we ask. Instead of asking only, how many ways can n be written as 4 squares? We can ask, what geometric structure is encoded by all those representations? Which symmetry orbits occur? Which cosets do they occupy? When does a half-integer shell appear? How does the shell change as n changes? And how does the corresponding structure appear in the D4 lattice? These questions take us beyond counting. They turn 4 square representations into a study of geometry, and they suggest that the shell itself should become our central object. For each, n, construct the shell. Enrich it with the half-integer representations when they exist. Organize it by symmetry, classify it by coset, and then study it simultaneously as arithmetic, quaternionic, and geometric data. This is the framework emerging from our examples. It brings together 3 subjects that at first seemed separate: Lagrange's four-square theorem, Hurwitz quaternion arithmetic, and D4 lattice geometry. The remarkable possibility is that they are not merely related, They may be different languages for describing the same underlying structure. We have seen this happen already at the smallest shell. The 24 Hurwitz units, the 24 roots of a D4, the vertices of the 24 cell. 3 descriptions of one remarkable configuration.